All right. Good morning, everyone. Thanks for coming to the first presentation of the tech track. So I'll be talking about a bit more technological stuff here. So I'm going to go a bit deeper in terms of the tech. If that's not for you, the other room has the main track where my colleague Des is speaking right now. My name is Christoph Dwertmann. I work for Vault Systems, and I want to talk about three different things today. First of all, I want to talk about the company, Vault Systems, very quickly, what we do, who we are. Then I want to talk about the information security manual from ASD and what it has to do with OpenStack, or how to secure an OpenStack cloud with the help of that. And thirdly, I would like to talk about Ceph. All right, let's get started. So, who is Vault Systems? We're a community cloud for Australian federal, state, and local government agencies. We've been founded 5 years ago, and we are running a OpenStack, obviously, otherwise we wouldn't be here. So, a customized version of OpenStack. We've heavily invested into some coding there to make it compliant with the ISM. We have completed our IRAP assessment to unclassified last year. That was successful, and now we are listed on the Certified Cloud Services list by ASD. We are providing an ISM-compliant cloud, a standard operating environment to our customers. So it's basically a pre-configured operating system that they can boot up, or actually a range of operating systems, which has been pre-configured to ISM rules. Protected level classification is coming soon. We've completed all the controls and the IRAP assessment on those. We're just waiting for the final sign-off from ASD on that one. And Secret is currently under development. We have offices and also data center presence here in Canberra, but also in Sydney. So, about the technology that we're using, we have a Intel Xeon platform. I think that's what most people are using these days. It's very high density. It's usually 2 machines per rack unit. 512 gigs of RAM on most of the compute nodes. We're looking into purchasing some larger nodes as well with a terabyte or more. We're in the process of putting in Mellanox 100 gigabit networking, which is it's very good. It has a few benefits for us. It reduces latency quite a bit as well. And we have recently deployed a pure NVMe Ceph cluster as our main storage backend. I'm going to be talking about that one later in the presentation. We also have Cinder LVM storage on flash for our best IOPS performance. That's ideal for databases and such. We're also running a multi-region Swift cluster. That's currently running on spinning disks, really high-density disks, usually 8 or 10 terabytes per disk, with 3 times replication across different data centers. And we're also in the process of adding icon connectivity to our secure internet gateway. We already have multiple redundant ISP connections, but especially for the folks here in Canberra, it would be interesting to have to directly connect to via icon to Vault. All right. The ASD Information Security Manual. Can I ask in the audience who has heard of this or who has seen this before? Almost everybody. That's good. So I can skip over these a little bit faster. So just for the people who don't know what it is, it's issued annually by ASD, and the objective is to help our government agencies in protecting their information and systems. In 2016, we saw 938 controls in it. There's a spreadsheet as well. It doesn't just come as a PDF. The spreadsheet is very, very helpful. So if you don't have it, ask ASD for it. It's a lot easier to read than the PDF pages, I find. Here's just a few words or a few keywords or a few headlines taken from the ISM, just to give you an idea on what it's covering. There's a lot of things around physical security, cybersecurity incidents. There's a lot of documentation required. So whenever there's an incident, it needs to be logged somewhere. A lot of documentation is definitely involved. Some other things around working off-site, for example, if you have staff who works from home, how to secure their machines and their access. Then a lot about media security, which I'll be talking in a bit more detail about, just to give you an idea what's in the ISM. And since Vault Systems is offering services to Australian government agencies, we have to be compliant with all the ISM controls, obviously. That's been done in 2015 for unclassified. We must continue to ensure compliance, even when there's a new manual. So every year, usually sometimes in March, April, there's a new ISM, and we just have to go through all the controls that have been added, removed, changed to make sure we stay compliant. We're offering our customers a compliant environment, as I said before. So a lot of the work's already been done for a customer who starts a virtual machine on Vault. It's already been hardened and pre-configured to the ISM rules. However, after the customer spins up the virtual machine, it's obviously their responsibility to keep it compliant, because the first thing many customers do would probably turn off some of the firewalls, maybe change the antivirus, and change a few things. At that point, they are responsible themselves for keeping the environment compliant. So. The ISM itself is obviously not something that came out of the cloud. It's been around for longer than the cloud's been around, I guess, or the cloud technologies. So it came from more like a traditional IT point of view. It's slowly adapting, though. We find that with every release of the ISM, we see a few new controls or a few modified controls. Some controls even get deleted to make it a bit more cloud-friendly. So, for example, the controls 1460 to 1463, they talk about the functional separation between the server-side computing environments. What this really means is virtual machines. So how do you separate the workload of two virtual or multiple virtual machines on one physical host from each other? So there's a few rules around that. Thankfully, the ISM is covering that, so we can do virtualization. Some controls are surprisingly difficult to implement. One of the things that we kind of stumbled over was email. Email is something that we basically didn't use very much in Vault internally. We just had like one older NetApp appliance which sent emails out, like an auto support email whenever a disk would fail. And in order to support that, we had to implement an email server and harden it according to the ISM rules. There's a lot of work being done around adding that the markers to the subject line in order to make sure that the classification of the outgoing emails is correct. This seemed to be quite a bit of work. So in the end, since we only had this one appliance that wanted to send email, we changed the settings for it to use HTTPS instead of email, and that just works fine. So in some cases, we found it's actually easier to, change the technology or avoid a certain subject in order to save yourself from some trouble. On the evaluated product list, that's a list that's been published by ASD regularly as well. There's a lot of hardware and software components listed on it that have been certified by ASD for government use. However, that list has a lot of outdated hardware on it, as you probably know, and also sometimes the software is fairly outdated. So we had some Juniper gear, for example, and the EPL told us to install a version of it which was pre-Heartbleed and it was basically years old and had a lot of security holes in it. But you basically have to start with that one, and then you have to upgrade it to the very latest version. But you have to pick a product that's on the list, and that's not always easy, especially when you're trying to build a modern cloud with like some modern components in it. We're using OpenStack from source, so we've got our own Vault distribution, if you will. This allows us to meet the ISM requirements by changing some of the source code. So we looked at some existing distros from different vendors, and we found that there have been some of the security controls have been implemented, but none of them were obviously specifically designed for the Australian ISM requirements. So we've had to modify quite a bit of code to make it compliant. And then obviously open source helps a lot with that. If you have a proprietary product, you don't really know what's going on inside. You'd have to wait for somebody else to evaluate the product and put it on the EPL. But with OpenStack, we can basically change it to the way we want it, so it can fit the security requirements. Some controls may not apply at all. This one, for example, talks about fax machines. We don't have any fax machines in our cloud, so I guess we can just ignore that. some controls are not so cloud friendly. For example, this one here talks about VLANs. So basically what this means, what this table means, is that if you have workload of confidential, protected, unclassified, for example, you cannot just simply separate these workloads by a VLAN ID. That's not good enough. That's not good enough isolation. So unfortunately, a lot of cloud products, or in the cloud world, a lot of people use VLAN or similar technologies like VXLAN, IPsec, GRE, or anything like that, to separate different types of traffic or from different customers. However, that's not good enough under the ISM. So if you have two customers that are both, let's say, protected, you can have them share the same network hardware, but you cannot have one unclassified and one protected customer basically using the same switch. This is not very cloud friendly because some of the cost savings that you have around cloud is that you can, all your customers can share the same pieces of hardware. But in this case, you basically have to build a secondary availability zone for your protected or for your confidential in order to keep things really separate. Now, you could say, I'm going to be smart and say, it says VLAN, so I'm going to use VXLANs in my cloud. But I think that's not going to fly with the IRAP assessor. Because the intention here is clear. It's like a software-based, like a tagging in order to isolate the network traffic. It's not good enough, not secure enough. All right. I want to give some examples about some controls from the ISM and how we implement them in OpenStack. One big section of the manual talks about media security. So there's a control that says agencies should sanitize all media prior to reuse. So if you have a Cinder LVM installation, you're basically mapping a piece of block storage directly to your customer's VM. Now, when that piece of block storage is then released by the customer, not used anymore, and some other customer then uses it, they could theoretically try and recover some of the data from that partition or from that piece of block device that was previously assigned to somebody else. So we obviously have to prevent that, and thankfully in this case OpenStack has a feature for that. So in the cinder.conf configuration file for Cinder, there's a function that says volume clear, and in volume clear you can say you can choose a few different options how you want to wipe your volume. I think the default is just to override it with zeros with DD. That takes a long time and it's not secure according to the ISM manual. The ISM says you have to override it 3 times with random data. There's a utility in core utils in Linux, which is called shred, which overrides a block device or a file with a random pattern taken from the pseudo random generator on Linux. And that works fairly well. It still takes a long time, the 3 times overrides, but, well, that's what it takes in order to make it compliant. So in this case, we didn't have to modify any code. This was already built in. So one question that we came across frequently in the data center, what do we do with a faulty drive? So if we have a faulty drive and we still have warranty on it, we'd like to get it replaced, ideally, without paying for a new drive. So what does the ISM say? Basically says you must destroy media types prior to disposal as they cannot be satisfied because they're faulty. So if you have a disk that's completely faulty, let's say the controller, the logic board is faulty, that you cannot even see the disk in the operating system anymore, you have to, unfortunately, you cannot re-RMA it. You cannot sell it. You cannot give it to somebody to have it exchanged. You basically have to destroy it because the data can still be reconstructed, and therefore that's not an option for you. However, if you can successfully sanitize your drive, sanitizing again, overwriting 3 times with random data, if you can successfully do that, it actually lowers the classification of the drive. So if you had previously unclassified DLM or protected data on your drive, after the sanitization process, it then becomes unclassified. So you can lower that a little bit. Another option to reclassify drives is to use encryption on the drive, data at rest encryption. So for data at rest encryption, there's many different options. I just listed 3 of them here. There's probably more. There's probably proprietary solutions as well. One's pretty simple one. Most disks that you buy today have a self-encryption feature. Basically, when you initialize the drive, you can set a data encryption key, which is stored on the drive's logic board itself. Now, if you want to then RMA the drive, the only thing you need to do is change that key, and all data becomes unusable. It basically becomes garbage data. Now, that will only reduce, again, your classification by one level, similar to this table here. So that's one option, but that obviously only works if you can still access the logic board. Like if the logic board of the drive has failed and you can't communicate with it, you can't issue that ATA command to it, you won't be able to change the encryption key, and therefore you can't sanitize the disk. You can't make trash the data on the disk by changing the encryption key. Another option is dmcrypt. This is Linux built-in disk encryption. It's pretty cool, but you got to be careful on where you store your key. Obviously, don't store it on the same drive or on another partition of the same drive. If you have it, if that's the only drive in your system, you may have to type in a key every time the machine boots. So that may not be as convenient, but it nevertheless is a way to do it. And a brand new feature that was just introduced in OpenStack Newton for everybody who's using Swift. Swift now supports object encryption. So the Swift proxy or the Swift object server actually adds encryption using the Python crypto library and encrypts before writing the object to the disk. It encrypts it and also encrypts the metadata along with it. That's actually pretty cool and very useful for everybody who's using Swift. There's no performance penalty because it uses some Intel encryption extension that are existent in most modern CPUs, most modern Intel CPUs. And that's a good way to encrypt your data on disk. However, you still need to sanitize the disk. So even if your data is encrypted and your key is not stored on the drive, you still need to sanitize it. So for Swift, for example, where they store the key is in OpenStack's Barbican key storage. That's on a different machine, that's somewhere else, so it won't be stored on the disk. But still, you have to sanitize. So the answer to the question is yes, you can RMA a faulty drive if the drive was reclassified to unclassified through sanitization or encryption and sanitization. And you also have to make a formal administrative decision in your organization to say, I want to release this particular unclassified media or media waste into the public domain. So there's a lot of buts and ifs, but if you read all the controls around it, you can figure it out. All right, so where does it lead us with the ISM? It's quite a bit of work to implement it. A lot of controls. Some of them are easy, some of them you can skip, but some of them are really a lot of work. And that's not where it ends. You have to obviously keep up to date with all the latest controls and keep updating your cloud to match them every year pretty much. Not all controls are cloud friendly. I could give more examples, but I don't think time will allow. Some creative ideas may be required to work around some trickier controls. The IRAP assessor can help as well. If you have a chat with your IRAP assessors, they can maybe make a suggestion. But generally, I find the ISM is best practice for IT security. It's actually a really good idea to implement those controls. First, when you see it, you think, oh, that's a lot of work, and why am I doing this? But after a while, you realize that most of these controls actually make a lot of sense and make your deployment in your system a lot more secure. But the good news is for any government agencies, Vault Systems already did most of the work for you. So if you are using a virtual machine or multiple virtual machines on Vault Systems, you've pretty much ticked most of these controls off your list already. All right, that's about the ISM, and now I want to move on to the next subject, the next part of my presentation, and that's Ceph. Who's heard about Ceph before? All right, yeah, that's a few people as well. It's a free software storage platform, free software, that's great. At Vault, we use a lot of free software. It's been in development since 2007, so that's actually been around for longer than OpenStack. So it came out of someone's PhD thesis, and it's been developed since, and Red Hat's been doing a lot of work on it, so it has really matured. It implements object, block, and file storage, and it runs on commodity hardware, which obviously is a great cost saver. You can basically run it on any type of server you want. You're not tied to any particular manufacturer or vendor. So pretty much any computer will do. It's fault tolerant, self-healing, self-managing, so it can really deal well with not just failed disks, but also entire failed servers. As soon as a failure happens, the data is automatically moved across the platform in order to keep the number of replicas up. This process is very fast and happens automatically, so in most cases there's not a lot of management that needs to be done in the case of a failure. And we haven't had any outages with it yet, so it's been running very smoothly. We are mostly using the block device or the block storage function of Ceph because it features some advanced functions such as snapshots. Like those are functions that you get on like more expensive appliances like NetApp. So snapshots is a cool thing. Striping for extra performance, and obviously native integration with KVM and Linux, because that's what we run in our cloud. There's a 6-month release cycle, so there's pretty active development and new software all the time. So anyone who's implemented Ceph before probably saw this slide before. Basically, on the bottom, Ceph is a object storage. It's called Rados. It implements object storage, and all the other services are implemented on top of object storage. So the Rados gateway is basically an interface or an API that provides REST-style S3 or Swift-compatible APIs. So if you're thinking of deploying a Swift cluster and you already have experience with Ceph, you might as well use Ceph for it, because you can use the same platform and it provides compatible APIs. So a lot of your applications that speak S3 or Swift can already talk to Ceph pretty much natively. The main function we use Ceph for is RBD, which is the block device driver. So with RBD, it basically maps a block device on top of a lot of objects. And KVM can talk directly to via librd and mount these block devices. And you can also mount them in Linux directly if you like. And the last feature is CephFS. It just recently became stable in the latest release of Ceph. CephFS is similar, it's like a network, like a shared file system, kind of similar to NFS, but I guess with a lot less hassle. I've tested it, it works well. It has support for Linux and Fuse as well, so some other operating systems will support it too. All right, so how does Ceph actually read and write data? So let's take the example of RBD. So you've got an application which does a read request. It sends the read request to the primary OSD. The OSD is basically a piece of software that runs on your servers. You can have multiple OSDs on your server depending on how many disks you have. Generally, the manual recommends to have one OSD running per disk. And so your read request is sent to the primary OSD, and then the return value, basically the payload, is then sent back to your application pretty much immediately. When you do the write, however, it's a little bit different. When you write some data to your Ceph cluster, it is first written to the primary OSD and then replicated to some other servers, so pretty much on different hardware, in order to make sure you have the number of replicas in your cloud that you want. So by default, I think it's a replica set to 3. So most people have 3 copies of each object that they're writing, of each block that they're writing in this case. Now, only after the writes are completed to all 3 servers, the reply is sent back to the application and says the write has been completed. All right, if we look at driver adoption for Cinder, this data comes from recent OpenStack surveys, where people have asked the community, what are you using for your Cinder? And there's a few vendors like NetApp, VMware, EMC, SolidFire, some big names. But as you can see, only maybe about 10% of the OpenStack users are actually using them in production in their cloud. LVM is a little bit more popular because it works across different hardware, different vendors. But the absolute king is Ceph. Ceph is really used by a lot of people, and I'd say anyone who's seriously thinking about OpenStack should also seriously think about Ceph, because it has a lot of features, it's very well supported, it's pretty stable, and it just rocks. So, why are we using it? Well, first of all, we like open source. We're an open source shop, so Vault Systems uses almost exclusively open source, except for a few exceptions where we had, due to the evaluated product list, there was no open source evaluated product on the list, so we had to pick something else. But wherever we can, we try to use open source software. We don't like to depend on a single vendor for support, RMA, upgrades. We've had a bit of bad experience there with NetApp. It was just basically what you're buying is like a black box. You don't really know what's going on inside of it. If there's something broken, usually you have to contact support. You can't fix it yourself unless you're a NetApp expert. But we'd like to be in control of our systems, and we'd like to at least try to fix all the problems that we encounter ourselves. There's also a very good community support in Ceph. So usually if you ask a question on the forums in Ceph, you get a reply much quicker than we would get a reply from our storage vendors. OpenStack integration is, I would say, second to none. It is integrated with Cinder Volume, Cinder Backup, Nova for authentication. We have Keystone. And it can also be used as a Swift alternative. So it really fits in with a lot of OpenStack services, and it's very, very, very well integrated. It's a large online community, as I mentioned before, very active development, very good. It's very versatile. As I said, we use it mainly for block, but you can also use it for object, or if you have any requirements for a shared file system. You can even, I think, integrate it with OpenStack Manila to offer people remote file system access. It's distributed, so we can actually upgrade, reboot, power off a server without our customers noticing. So no downtime on upgrades, which is great. A lot of the commercial solutions have that too, but it's still nice to have on Ceph. And copy on write is a cool feature which allows us to instantaneously spin up an instance. So we've seen some Cinder drivers where it took quite a long time to make a copy from glance into Cinder, but with Ceph, you can basically spin up a large instance, let's say an 80 gig or 100 gigabyte volume, pretty much instantaneously because it uses this copy on write internal feature. All right, so I want to talk about our Ceph cluster. I believe that this is one of the first, if not the first, pure NVMe Ceph cluster in the world. We've talked to a lot of people. I don't think anyone's done it before us. There's more people doing it right now. The reason why we went with NVMe was because there was just a recent price drop. It dropped down quite a lot. It used to be a lot more expensive than SSD. Right now, not so much anymore. So we decided to go with that, try to get a lot of advice on how to dimension and how to size this. And that was really a problem because since most people were building Ceph clusters that are either purely on spinning disks or a mix of spinning disk and SSD, we really struggled to get the right dimensioning done for ourselves. So for the monitors, we've got 3 monitors with 8-core CPUs, 64 gigs of RAM, Intel P3700 NVMe drives. Those drives are insanely fast. I believe those are the fastest drives that you can buy right now. They're PCI Express, and they're very expensive. We only got the 400 gig version, and that is for that level DB, which is stored on the monitors. But after putting that into production and monitoring the load on this box, it basically has nothing to do. Like we overspec this one, and this is definitely a mistake that we made. Well, not the worst mistake to make, better than underspecking it, I guess. But for the next monitors, we'll definitely be revising that. But still, nevertheless, the monitors perform very well. For the 4 OSDs, we've got 4 right now. It's going to grow in the future, obviously. We've got 16 cores of CPU, which seems about right. 64 gigs of RAM, and 10 times the Intel P3600 NVMe drive with 2 terabytes. That drive is connected via the U2 connector. It is not a PCI Express drive because we didn't want to buy these massive servers that have lots of PCIe slots in it. So those servers are, performing very well. Total cluster size is around 74 terabytes. We've got 2 replicas, and we're using 20 gigabit bonded networking with the transmit hash policy set to layer 3 and 4. This is just an optimization that we did, which gave us the best performance. To deploy it, we're using a project called Ceph Ansible. So there's the link to GitHub here. If you've have not heard about it yet, you can check it out. Ansible is a tool which, similar to Chef and Salt and Puppet, which allows you to deploy your software across many machines in the cloud. We use that to deploy OpenStack, and pretty much everything in Vault is deployed with Ansible. And therefore, we thought, Ceph Ansible, that's awesome. That's already a project, so we don't have to code that from scratch. And yeah, it is really great. Basically, you clone that repository, you change a few values in some YAML files, and you're good to go. Ceph Ansible does absolutely everything for you. You need to install the OS. We use canonical mass for that. And after the OS has been installed, we can run Ceph Ansible. Ceph Ansible does everything. It detects the NVMe devices, formats them, partitions them, creates the journal, creates the XFS file system on it, and then it deploys the OSDs and the monitors and pretty much all the services that you like. If I buy that same hardware that we have today, if I would buy that again, I would be able to bring it in production after the OS installation, maybe in 15 minutes. So Ceph Ansible runs really, really fast. Very cool project. We've been actually contributing to that project as well. So the guy who's running this is very friendly. He's very happy to accept pull requests. To benchmark, we use FIO. That seems to be the industry standard to benchmark Ceph. Inside the KVM, we use the AIO plugin. Outside, we use the RBD plugin to directly talk to librd, which gives us a bit extra performance on the bare metal. Yeah, so what do we observe for performance? It's first of all sequential read and sequential write. The bottleneck was very clearly the network. So we managed to saturate all 4 20 gig ports that we had on our OSDs. We had a total throughput of 7.5 gigabytes per second, which is pretty much, fully loaded 4-port 20 gigabits. So that's clearly the bottleneck. I can't help but wonder what it would perform like with faster networking. We're in the process of installing some Mellanox gear, so hopefully we'll find out soon. For the random read performance, random read 4K, we've got more than 500,000 IOPS measured from bare metal. This is actually, to us it's a pretty impressive number because previously we were running NetApp and that box gave us 10,000 IOPS. So going from 10,000 to 500,000 was obviously a massive jump. Our customers love it. We love it too. But there are some other products in the market from, for example, SanDisk. I know that they are selling a Ceph cluster sort of appliance, which has more than 1 million IOPS, so 1.2 million, I think they're claiming. Why is that? Why are we not getting this on NVMe? And the reason is that I talked to some people who have implemented Ceph, and they told me that if you have more than one OSD per disk, for example, 2 OSDs per SSD or 4 OSDs per NVMe drive, you actually get better performance out of it. Heaps better performance. The reason is because the NVMe drives can really handle parallel writes in multiple spaces on the disk at the same time very, very well. And therefore, having more than one OSD per disk is recommended if you want maximum performance. On the KVM side, like inside the virtual machine, we noticed that we're actually limited to 50,000 IOPS per KVM. This was actually initially 35,000 IOPS when I started playing with it, which was a bit disappointing. I was like, why am I not getting more than that? I spoke to some members of the community and I got some help from the mailing list as well. This is due to the way the librd is allocating memory with malloc. There are some faster memory allocation libraries. There's one called tcmalloc and one called gemmalloc. One is developed by Google, I think, to sort of speed that up. So when linking KVM and librd against gemmalloc, I was able to boost that from 35K IOPS to 50K IOPS on a single VM. But that seems to be the ceiling. As I said, I was in Barcelona 2 weeks ago in the conference, and I spoke to a couple of people there, and they mentioned that they were facing the same issue on KVM. So this is a limitation in KVM librd, which will hopefully be lifted in a future software update. Our latency is around 1 millisecond. Cinder LVM still beats that because Cinder LVM is basically just iSCSI directly to a piece of block device. Whereas on Ceph you have a bit of extra things in the middle. You've got the crush algorithm, you've got the monitors, you've got multiple things that need to be contacted. So the latency is a little bit worse. So it's still good for database workloads, but for best performance we currently recommend our users to use Cinder LVM. All right, so what's in stock for the future for Ceph? What we'd like to do is we'd like to patch Ceph Ansible to support more than one OSD per disk fully automatically. So ideally there should be a configuration option to say, okay, 4 OSDs per disk, and it will fully automatically deploy. For optimal performance, that's what we're going to do in our next cluster. We're moving to converged store compute and storage architecture. Previously, we were using separate machines for Ceph NVMe, but now in the future, we'll be putting those NVMe drives directly into the compute, therefore saving rack space and obviously, hopefully, getting even better performance out of it. RDMA is a pretty cool feature which is supported by some network cards, Mellanox being one of them. RDMA is also now supported in the latest Ceph release. We're hoping to shave off some of the latency with that and therefore improve our IOPS. And last, there's a new file system type coming. It's called BlueStore. It sounds like an IBM product almost, but it's actually something that's developed by Ceph. And so right now you format your Ceph drives with XFS or ext4. In the future, you can use BlueStore in order to format it to Ceph's own file system type, which they claim gives you a 100% performance boost, so twice as fast. That'll be ready in production probably in the next release of Ceph. All right, and this concludes my talk. I've just got some credits here because I took some slides from some other presentations. And yeah, that's the end of it. If you have any questions, please ask. Otherwise, this is my email address and our website if you want to have a look.
Brilliant. Round of applause to Chris, please. So we've got a couple of minutes. If anyone would like to ask any questions of Chris, we've got one right here. Let me grab you a mic because we are being recorded.
I've got a parade voice. Oh, okay. Sorry. Chris, John Hodgson, I've lived with ISM and its predecessor, Axie 33, for 30, 40 years now, ever since I started as a youngster with IBM, God knows how long ago. Mm-hmm. I might note the development cycle of the OpenStack and Ceph and so forth is 6 months. Mm-hmm. The ISM is only reviewed every 2 years mm-hmm. on the current cycle. Mm-hmm. So it's always going to be out of date.
Yeah.
The EPL, or the evaluated product list, comes from a common criteria evaluation, mm-hmm. which typically the vendors are responsible for. With open source, it's a problem because a vendor has to take responsibility
yep.
to get a certified evaluator to do that.
Exactly.
And that's why it's always behind. The EPL is just a record of what has been evaluated.
Yeah.
Red Hat overcame it, partly because they were selling into NSA with Linux, so you can get a good V1 version of Linux out of Red Hat. Mm-hmm. Oracle's catching up on Linux, but this area, OpenStack and so forth, is a long way behind, and my view is it's unlikely to get evaluated products in the timescale we're talking about. Mm-hmm. The only alternative then you've got is to do a thorough risk assessment, right, by a qualified IRAPper or someone who
yep.
actually knows what they're doing.
Yeah.
ASD, NSA and GCHQ will accept a good risk evaluation of what the actual risks are and how you mitigate them. So you can work your way around it. Yes, it's convoluted and it's a pain in the neck, but I've done it in the past inside defence systems. I even did it inside DSD when I was their leader-C for IBM in the 90s. So you can do it, but you're correct. It's a pain in the neck.
It's a pain, yeah, but we're working on it. We've implemented all the controls. We went through our IRAP assessment, and that all went pretty well. Our auditor is happy with it.
Big step up to secret, though.
Yeah, we're working on it. We're working on it.
One question from the Always lovely, Michael Still.
This is totally unfair, right? So as an upstream guy, how painful do you find forward porting the patches you have against OpenStack to a new OpenStack release?
Well, if you design them properly and you keep the diff files around and you keep track of what's happening in master, it can be painful at a time, but some of the things haven't changed in a while as well, so it really depends on where you're making your changes. I agree. It's always a pain, but we have to do it if we want to run our custom OpenStack.
Well, have you considered pushing any of those patches upstream?
We have actually pushed some of these patches upstream. Anything that we thought was relevant to the community and could help other people, we have pushed.
Okay, cool.
Excellent. So we're at morning tea, but let's give Chris one more round of applause. Thank you so much, Chris, for coming today. Really appreciate it.